Hey guys, welcome to the next video. In this one we're going to be illustrating how to graph a derivative based upon what the original function looks like. In order to illustrate this, I'm going to show you guys this Desmos file I created. In this file we have a couple lines. First of all, we have a red line, which is going to be our function f of x. In this case I've set f of x equals 2, which is why it looks like just a horizontal line right down there. If you guys have never seen this before, those curly brackets are something you can use to constrain the domain of your function. In this case, I'm saying I only want to show my function between an initial value a equals -4 and a final value b equals 4. Next, we have this slider here for x sub I. And what x sub I is going to be is that's going to take on any value between our points a and b. So I can just move it between -4 and 4. And you'll see that if I do that, those 2 points, the red point and the blue point, will move according to what that xi value is. Now, if you look down here at the blue function is the derivative of f of x. Okay, we call it f sub p for f prime of x. So remember the terminology that we use when we're describing a derivative. In this case, I've said that the derivative is d over dx of f of x. Remember, d over dx of f of x is saying the function f prime of x will be the derivative of f of x. Okay? Now, in this function, I'm constraining it a little bit different. If I highlight it, you can see it a little bit better. But it's only going between the initial point a and the point xi, which is why when I move my slider around like this, that's why the blue line only goes between where the blue point is and the initial point, and the red line goes all the way to that final value of b. But yeah, anyway, so if you've never seen this derivative feature in Desmos, it's really useful. However, I want to describe it to you with a bit of caution. You should use it as a way to get you to understand derivatives or to check answers. Please do not use it as a crutch, though, because you will find yourself in a really bad situation come test time when you don't have Desmos right there to answer some of these questions related to graphing derivatives. Okay, so first off, if we look at this, if we see our function of f of x equals 2, well, that's just a horizontal line. And what is a derivative again? A derivative is a function that represents the slope of the line tangent to our curve at any point. Well, if f of x equals 2 is just a horizontal line, what's the tangent line going to look like? Well, the tangent line is always going to be 0. It's always going to have a 0 slope. So that's why when we drag our slider across here, our derivative, or the blue line, is always 0. All right? So now let's switch things up a little bit, and let's change our function to 2x. Okay? Try to see, while I erase this stuff, if you can predict what the derivative function is going to look like if our other function is equal to 2x. Okay? So again, a derivative is the slope of the line tangent to the curve. Okay? So what is a line tangent to the curve of 2x going to look like? Well, the tangent line is always going to have a slope of 2. Okay? So if we plot the derivative forward in time, no matter where we are, that derivative is just that constant line, or the blue line is just a horizontal line at y is equal to 2. Okay? So we did ones like this in the previous video, so this shouldn't be too confusing. But now let's change our function to be something that's quadratic. So we'll call it 2x squared. Okay? Now see if you understand why the derivative looks the way it does. We did this one in a previous video as well, but see if you can get it now. Let me zoom out a little bit. And let me use another function here that I created, this t of x function, which will illustrate the line tangent to our function or our red curve at any point. So let's look at this right here, okay? We got that the black dotted line, or the line tangent to our curve right here, that's got a really steep negative slope, okay? Look at where our blue dot is. Look at what our derivative is. It's a really big negative number, okay? Now, as I move this slider forward, what's happening to the slope of that black dotted line? Well, you should have seen it's gotten shallower and shallower as I've moved from x equals -4 to x equals closer to -1, okay? Look at what the blue line has done. As the slope of that black line has gotten shallower, the blue line, while it's still staying negative, is getting less and less and less negative, okay? So when we move it all the way to x equals 0, well, what is the slope of our tangent line? The slope of our tangent line is 0 right here. Now, if we zoom in on our function, we'll see the derivative hits 0 at that point because the slope of our tangent line is equal to 0 right here. And this illustrates a very important point of when we know when a derivative is equal to 0 graphically. If we have a hump like this or like this, these x values right here are going to be associated with vertical tangent lines. Notice also that in both of these cases, the tangent line to the left and the right of that horizontal tangent are different signs. Here we have a positive slope and a negative slope. Here we would have the opposite. We would have a negative slope of the tangent line and a positive slope of the tangent line. So whenever you have a hump, at this point of the hump, you're always going to have the derivative is going to cross the x-axis. It's going to switch from negative to positive or positive to negative. Now, in a similar note, if we had something maybe like an x cubed curve that looks something like this, you know, somewhere, actually I should have drawn those to be a little bit more horizontal. Let me do that again. There we go. So if we had this curve, well, we'd have a horizontal tangent right here, but notice that the tangent line to the left of it is positive and the tangent line to the right of it is also positive. In this case, at this x value, our derivative would be equal to 0, but it wouldn't cross the x-axis. It would just touch it and then bounce off. Likewise, if we had a plot that looks like this, our slope would be negative. Then when we hit this point, the tangent line would be 0, but then it would go back to being negative. So when you have something like this, you get a derivative touches the x-axis, but when you have humps like this, you get the derivative crosses the x-axis, okay? That's kind of a nifty little trick that you can remember to help you graph these things, all right? So if we go through and we trace out this function right here and we continue to do it, well, what's going to happen when I move that slider more forward to the right? Well, the slope of our tangent line becomes, positive, and it gets more positive the more we go towards that x value, x equals 4, and so our blue line goes up, okay? So let's switch things up once again. Let's look at x cubed, okay? If I move my slider down, let's check out what happens when I zoom out a little bit. We see that we start here at that point x equals -4. Our function has a absolutely gigantic positive slope, okay? Which is why our blue line starts as a very big positive number right there, okay? Now, when I move my slider towards x equals 0, my slope starts getting shallower and shallower, which is why the blue line starts moving down, all right? The derivative is getting less and less. And as I keep moving towards 0, it gets shallower still. The blue line keeps moving down. Now, this is what I was just describing. Look what happens here, okay? The slope of our tangent line is positive, and it's getting shallower, shallower, hits 0, but then it goes back to being positive again, and then starts getting steeper, 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 which is why our derivative curve, the blue curve, just goes down and touches the x-axis, but then goes back up. It doesn't actually cross it. Okay. Now, hopefully, some of you might have noticed a little pattern that's developing as we're looking at these functions right here. Okay. So let's go all the way back to the beginning. Let's look at a constant. All right. When we graph a constant, the derivative of a constant, let's unhighlight that, is going to be 0. Okay. If we switch from a constant to a linear function, the derivative becomes a constant. And this could be 2x plus 1. It doesn't matter. It wouldn't change the derivative. That's still a linear function. Then when we switch to a quadratic function, the derivative becomes linear. Then when we switch to a cubic function, the derivative becomes quadratic. You should start seeing a pattern developing here. This pattern underlies something called the power rule, which is something we will use in the next unit to aid in our calculation of the derivative, so we don't have to use that ugly difference quotient every single time we want to calculate a derivative. All right, so let's just stick with a cubic function right here, and let's do something like this, okay? So let's look at our derivative with a function like this, and let's highlight that tangent line again. So again, down here, we start off with a super big positive slope. So our derivative starts as a very positive number. That positive slope gets less and less and less and less and less until we zoom in. We approach this hump. The second we hit the hump, it's going to hit 0 because it's getting less steep and less steep. Then it goes from a positive slope on the left side of a hump to a negative slope on the right side of the hump. So we cross the x-axis, the derivative or the blue line crosses the x-axis. Now it gets negative, more steep negative, more steep negative, more steep negative. Notice the blue line drops down until we get to the steepest point. Then it starts getting shallower. The blue line starts moving up towards the x-axis again. Then we hit 0. Go from a negative slope to a positive slope, so it crosses the axis, and then we get more positive, more positive, more positive. Okay? Now let's look at something a little bit crazier. Let's look at the function sine of x. And now if we look at that, let's check this out. Okay? Our derivative, in this case, what's it going to be? Well, if the slope of the tangent line is negative, the derivative is negative. That's why the blue line is, or the blue dot is negative. Now, as we move further down, it gets steeper negative. Notice as it gets steeper negative, the blue line goes down. It gets more negative. Okay? Then we get shallower negative, so our blue line becomes less negative. Right here, we hit 0, a horizontal tangent, and we switch from a negative slope to a positive slope. The blue line crosses the x-axis. We go back up, steeper, the blue line goes up. It gets more positive. Gets to about its maximum value here, then it starts getting shallower. It starts moving down towards the x-axis again till it hits 0. And here we have a cross between a positive slope and a negative slope. So again, the blue line goes from a positive value to 0 to a negative value. And then we get steeper negative. The blue line goes down until we start moving back up again. Okay, so hopefully seeing this should help you understand how you graph a derivative based upon its function. In the next video, we'll look at doing the opposite. What if I gave you a derivative? How do you graph what the actual function looked like?